When designing a digital computer system, the CPU is usually connected to its memory modules by a series of interconnects known as the data bus. For convenience, simplicity, and economic considerations, the interconnects are usually connected in such a way that each memory bit always traverses the same physical line between the CPU and memory module. It's also common to extend this strategy across the component level where groups of bits are immutably wired to physically distinct memory banks. In this particular example, the 32-bit data bus is physically connected to 4 discrete 8-bit memory banks. Simplifying the example for convenience, we present a 16-bit CPU connected to 2 discrete 8-bit memory modules. As the CPU always performs 16-bit data transfers, odd and even bytes are physically locked to the most and least significant halves of the memory bus respectively. This results in an interleaved 16-bit aligned address space, where adjacent memory bytes are concurrently transferred across the 16-bit data bus. Therefore, when the CPU wishes to access an aligned 16-bit word, it simply transfers associated rows across the least and most significant portions of the memory bus. Conversely, if the CPU wishes to access the least significant byte in isolation, it again transfers the entire 16-bit row and discards the most significant portion of the transport. Analogously, if the CPU wishes to access the most significant byte, it performs the same 16-bit transfer and instead discards the least significant portion of the transport. Finally, if the CPU wishes to access an odd-aligned 16-bit word, the requisite data is divided across multiple 16-bit memory rows. Consequently, the requisite bytes cannot be transferred in a single 16-bit memory cycle. Whilst some architectures will not allow odd-aligned memory operations of any kind, others will access the data by implicitly issuing multiple consecutive memory cycles. Unfortunately, as C was initially designed for speed, it does nothing to standardize the way in which disparate architectures perform misaligned memory requests. Examining this code a little more closely, it should be readily apparent that a misaligned 16-bit transfer occurs when the buffer is aligned on an even memory boundary. Whilst this function operates without issue on multi-cycle platforms like the 8086, it causes fatal bus exceptions on more rigid architectures like the Sun UltraSPARC. Ignoring numerical endianness for convenience, it is therefore necessary to manually decompose packed multi-byte transfers into single-byte memory operations. In this particular example, the 16-bit transfer is decomposed into 2 discrete 8-bit memory operations. Whilst this approach is guaranteed to work on all architectures, it should be noted that it is a suboptimal solution for platforms that implicitly support multi-cycle memory requests. Fortunately, many cross-platform compilers often implement non-standard extensions in order to specify packed data types in an architecture-independent manner. For example, when developing within the GCC toolchain, the packed attribute may be specified in order to generate the optimal safe code for the targeted architecture. As the C standard is unspecific with regard to packed data types, it's important to remember that misaligned memory pointers should always be considered a non-portable solution.